Problem 31. A closed tank contains layers of fluids as shown in the figure. It is hinged on the top portion and is held by a stop at the bottom. The gate is 1.5 meters into the screen. Determine the resultant force on the side of the gate, the location of this resultant from the hinge, and the reaction on the stop. So this is the figure. The best way to solve this, because the entire gate is in contact with three different layers of fluids, is the pressure diagram. However, I'll present my way of solving it to compare the results. But the best way is the first solution. So let's draw the free body diagram showing the pressure diagram. So this is 10 kilopascals. Then between this layer and this layer here, the pressure at this interface is supposedly 10 plus P1, where P1 is specific weight of oil 0.8 times 9.81 times 0.9. I will compute that later. Then the pressure at the bottom, maximum pressure at the bottom, is 10 plus P1, which is 0.8 times 9.81 times 0.9, plus this P2 here is specific weight of water times 1.2. So that's the total pressure at the bottom. So for this rectangular pressure diagram, we will call that F1. The total height of the tank is 0.6 plus 0.9, 1.5 plus 1.2, 2.7. Because this is rectangular, half of 2.7 is 1.35 meters from the top. Its moment arm. F2 for this triangular pressure diagram. Then the location of F2 from this interface of air and oil is 2/3 of 0.9. 2/3 of 0.9 is 0.6 plus 0.6, so 1.2. Distance of F2 from the top is 1.2 meters, so it's shown here. F3 for this rectangular pressure diagram of intensity P1. Then the height is 1.2, so this is half of 1.2, 0.6 plus 0.9, so 1.5 plus 0.6, 2.1. The distance of F3 from the top is 2.1 meters. And finally, for this triangular pressure diagram with intensity P2, from this interface of oil and water, 2/3 of 1.2, 2/3 of 1.2 is 0.8. So I'll call the force as F4. So distance of F4 from this interface is 0.8, 2/3 of 1.2, 0.8 plus 0.9, 1.7 plus 0.6, so 2.3 meters. So everything is set up. This is Fs, the reaction on the stop, and the probable location of the resultant force would be somewhere here. So F is equal to F1 plus F2 plus F3 plus F4. So that's the probable location of F, and we will call its distance from the top as y sub h. Then let's apply Varignon's theorem later to solve for y sub h. So F1 is volume of pressure diagram. By the way, P1 is 0.8 times 9.81 times 0.9, so 7.063 kilopascals. P sub 2 is 9.81 times 1.2. Specific weight of water times 1.2. Just this pressure for this triangular pressure diagram, 11.77 kilopascals. So we can now compute F1. F1 is 10 kilopascals times height 2.7, then perpendicular to the board 1.5. So volume of this pressure diagram is area of rectangle times 1.5. So 10 times 2.7 times 1.5, 40.5 kilonewtons. F2 for this triangle, area of triangle times 1.5. So area of triangle is half or 0.5 of P1 7.063 times height of triangle, 0.9, then perpendicular to the board, 1.5. So F2 is 4.768 kilonewtons. F3, represented by this rectangular pressure diagram, it is P1 times height, 1.2, perpendicular to the board, again 1.5. So it is 7.063 P1 times height, 1.2, times perpendicular to the board, 1.5. So F3 is 12.71 kilonewtons. Finally, F4 is 1 half of P2, or 0.5 of P2, which is 11.77 times height, 1.2, and perpendicular to the board, 1.5. So F4 is 10.59 kilonewtons. Finally, F is equal to 40.5 plus 4.768 plus 12.71 plus 10.59. So F is 68.57 kilonewtons. Then the location of this resultant from the hinge, we use Varignon's theorem. The moment of the resultant is equal to the sum of the moments of its components. So 68.57 times YH equals F1 40.5, distance of F1 from the top is 1.35, plus F2 4.768, its distance from the top is 1.2, plus F3 12.71, its distance from the top is 2.1, and finally plus F4 is 10.59, distance from the hinge is 2.3. So we can now solve YH. YH is 1.625 meters. Then finally, the reaction on the stop. So summation moment about the hinge equals 0. Fs times 2.7 equals F times YH. So we represent all these four forces by the single force F, the resultant, by Varignon's theorem. So Fs times 2.7 equals F 68.57 times YH 1.625. So the reaction on the stop is 41.27 kilonewtons. So that's it supposedly for this problem, but I want to share my own way of solving it to prove that my way of solving it is also true, no? Especially for complicated cases. Now, what if the gate is not rectangular? If the gate were not rectangular, then it's difficult to analyze the gate in this manner. So I'll use my own way of analyzing it. That is pressure at centroid times area. Then we'll solve for E sub V for its areas. So this is the FBD. There are only three forces. In my own way of analyzing it, we have force in contact with the gate where air is in contact for fluid 1, then oil, then water. These points are the center of pressures. Then we have EO, EW, centroid to center of pressure. Remember, there is E. Then for air, because the pressure in the airspace is uniform, there's no E. It acts at the centroid of the area in contact. So if the height is 0.6, then its distance from the top is 0.3. The distance of FO from the top is 0.6 plus 0.45, half of 0.9, centroid, plus EO. The distance of FW from the top is 0.6 plus 0.9 plus another 0.6, half of 1.2, plus EW. So that's it, because we have to solve for EO and EW later. So we use force equals pressure at centroid times area. This is the location of F, and this is Fs. Distance from the top is also Y sub H. So F, force of air, is pressure at the centroid of air times area of air. Now the pressure at the centroid of air, because this is constant, so the pressure is always 10. So 10, and the area of air is 1.5 perpendicular to the board times height 0.6. So it is 10 times 1.5 times zero point 0.6, 9 kilonewtons. Another way to prove that E of air is 0, or there's no distance between centroid of area and center of pressure in the airspace, it's because supposedly pressure in air 10, we equate it to specific weight of air, which is very, very low, zero point 0 something, times barred h of air. So barred h of air would be very, very high. Now in the formula, height of rectangle square, zero point 0.6 square over 12 times barred h of air, which is very high, that would be almost 0. So that's why E of air is negligible. I hope you understood it. F of oil, pressure at the centroid of oil times area in contact with oil. Pressure at the centroid of oil is, beginning here, 10 plus 0.8 times 9.81. We go down by 0.45, only half of zero point 0.9, to reach the centroid of area in contact with oil. So 10 plus 0.8 times 9.81 times 0.45. I hope you understood why 0.45, to reach the centroid of the area in contact with oil. Then area is 1.5 perpendicular to the board times height of the oil, which is 0.9. So I will compute this first, pressure at the centroid of oil, because we need that to solve for barred h of oil later. So it is 13.53, then area 1.5 times 0.9. So it is 18.27 kilonewtons. Then force in the water contact, so pressure at the centroid of water times area of the portion in contact with water. So pressure at the centroid of water, which is here, is beginning here 10, to make it clear here, 10 plus 0.8 times 9.81 times 0.9, then plus 9.81 times 0.6, only half of 1.2, because that's the centroid of the area in contact with water. So it is equal to 10 plus 0.8, 9.81 times 0.9 plus 9.81 times 0.6, half of 1.2. That's the pressure at the centroid of water. Then area 1.5 times height of water, or height of the gate in contact with water, 1.2. So F of water is equal to 22.95. This is the pressure at the centroid of area in contact with water. Then area of the gate in contact with water, 1.5 times 1.2. So it is 41.31 kilonewtons. Therefore, F is equal to F of air plus F of oil plus F of water. So 9 plus 18.27 plus 41.31. And it is equal to 68.58. So they are practically equal. It's because of rounding off the values of pressure, of course. So they are equal. Next is this one. But we need moment arms of F of oil. F of air is already 0.3. F of oil is 0.6 plus 0.45 plus E of oil, while the moment arm of F water from the hinge is 0.6 plus 0.9 plus another 0.6 plus EW. So let's solve for EO and EW. So pressure at the centroid of oil is 13.53. Equate that to specific weight of oil times barred H of oil to solve for barred H of oil. So barred H of oil is equal to 1.724. Therefore, E of oil, which is height of rectangle, 0.9 square over 12 barred H of oil. So E of oil is equal to 0.03915 meter. Then pressure at the centroid of water, 22.95. Equate that to specific weight of water times barred eighths of water because it is water in contact with the gate in this portion here. So 22.95 equals 9.81 times barred eighths of water. So barred eighths of water is equal to 2.339 meters. So let's move this so that you can see the solution in this one slide only. So E of water equals height of gate in contact with water 1.2 square over 12 barred eighths of water 2.339. So it is 0.05130. We can now use Varigdon's theorem to solve for YH. 68.58 times Y sub H, summation moment there, equals sum of moments of the components. There are only two components. Air, 9, moment arm 0.9, 0.3 rather, plus F of oil, 18.27. Its moment arm from the top is 0.6 plus 0.45, half of 0.9 plus EO. 18.27, 0.6 plus 0.45 plus EO. Hope you understood it. Plus F of water, 41.31. The moment arm is 0.6 plus 0.9 plus 0.6 again, half of 1.2 plus EW. So 41.31 times quantity 0.6 plus 0.9 plus 0.6 plus 0.0513 E sub W. So using your calculator there, you'll get YH equals 1.625. It's the same. And the last one, it's the same. Fs times 2.7, summation moment about the hinge equals F 68.58. I just use this result here times 1.625. So F sub S is 41.275. They are still practically the same. That's it. I hope that you gain additional knowledge in attacking problems, especially for this very challenging problem here. But the best solution is the first one. I'm just presenting mine because this second solution is best for very challenging problem. What if the area is not rectangular? What if it's not rectangular? Then it's difficult to apply this first solution. The second solution will be suitable for very complicated situations. That's all.